Good morning. Today we will begin our third chapter on integration and expectations. So, we have completed two chapters. The first one was on probability measures and probability spaces. The second one was on random variables. Now, this is the third chapter on integration and expectation. So, you are already familiar with integration, right, and the integral you are familiar with is known as the Riemann integral, right. This is from your calculus course, right. So, when you say integral a to b f of x dx, you know what it means, right. So, you take some function from r to r and you know how to integrate it over an interval, right. So, everybody is familiar with this. So, in particular, so you have some function f of x and you have some interval a to b. The way this integral a to b f x dx is defined is by dividing this x axis into several little intervals. So, let us call this each of this, let us call this delta x I, all right. So, this is x naught is a, x 1, x 2 and so on, right. This is x n minus 1 and then this is x n equal to b, right. So, you make a partition of the interval a b into these tiny little delta x I intervals. So, delta x I is simply x I minus x I minus 1 and then what you do, just to give you a quick refresher on what Riemann integral is. So, you take the following, you define so u n of f is equal to sum over I equals 1 to n supremum f of x over this interval times delta x I, but delta x I is simply x I minus x I minus 1. So, you define that and then you define ln of f as the same thing with an infimum of the same thing. Okay. So, essentially what you are doing is if you consider a particular delta x I interval, you consider the supremum of all the values taken by the function in that little interval, right, is the biggest value. So, in this case it is here and you may, and then for each such delta x I interval you consider this and sum multiplied with delta x I and sum it over I equals 1 to n. Similarly, for the infimum, right, this sum is called the upper Riemann sum, this is called the lower Riemann sum. Okay. Now, what you can show is that when n becomes bigger and bigger and the partition becomes smaller and smaller, the upper Riemann sum is monotonically decreasing. Is that clear why it is the case? So, if you want to draw a more magnified view of what is going on here, right, let me just draw a magnified view. Suppose that is my delta x I. Okay. So, I have a particular n and a certain partition. So, in this case I will have the supremum is here, this value, and the infimum is, let us say, that value, right. So, in the supremum I will substitute that value for this particular interval, right. However, if I create a finer partition with a larger n, so let us say I will have a further partition of this. Now, what will happen is I have, so for this interval, for this partition I will have that as my supremum, but this interval I will have a lower value as my supremum, right. So, when I do the upper Riemann sum with a finer partition, I get a value that is smaller, at least no bigger, right. And similarly for the lower Riemann sum, as n becomes bigger and the partition becomes finer, I will get a larger value. So, the lower Riemann sum can be shown to be a monotonically increasing sequence and the upper Riemann sum is monotonically decreasing. Okay. So, for this sum, for these, if you send n to infinity such that each delta xi goes to 0, right, this sequence must necessarily attain a limit, right, because this is a monotonically decreasing sequence and this is a monotonically increasing sequence, correct. For the moment let us assume that f is bounded. Okay. Is that clear? So, since u n of f is monotone decreasing and ln of f is monotone increasing in n, limit n tending to infinity u n of f and limit n tending to infinity ln of f must both exist right. Is that clear? Any questions on that? So, this is something you should already know, right. I am just reviewing Riemann integration. So, this limit and this limit definitely exist, right, but it is also the case that for every n u n of f is bigger than or equal to ln of f, for every n that is true. Why? By definition, right. So, so this limit exists and this limit exists as n tends to infinity. So, the limit of this must be greater than or equal to the limit of that, correct. So, this limit is known as the upper Riemann integral of f over a to b, okay, and this is known as the lower Riemann integral of f, this limit. Okay. This limit exists as real numbers and this is called the upper integral and this is called the lower integral of f. And f, the function f is said to be Riemann integrable if the upper Riemann integral and the lower Riemann integral have the same value. Okay. So, f is said to be Riemann integrable over a b if limit u n of f is equal to limit n tending to infinity ln of f. So, what we are saying is that ln of f is a increasing sequence in n and u n of f is a monotonically decreasing sequence in n. They must both have some limit. The limit may not be the same, okay, but if the limit is the same, if the limit and this limit are equal, in other words if the upper integral and the lower integral are both equal, we say that f is Riemann integrable over the interval a b, okay, and this common value is known as the integral of f over a to b. Okay. This common value is called, so this common value is denoted integral a to b f of x dx. Okay. That is your Riemann integral. So, is everybody familiar with this? So, one nice thing about this Riemann integral is that, so if f is Riemann integrable, it does not matter how you, so how you create this partition is irrelevant. You can create equal partitions, unequal partitions, any whichever way you like, and as long as each delta xi goes to 0, you have the same value of the integral. Okay, that can be shown. Any questions? And for a Riemann integral, if you have something like integral a to infinity or integral 0 to infinity of x dx, it is just like sending b to infinity, right. So, integral a to infinity f x dx is simply defined as limit b tending to infinity integral a to b f x dx, right, that is an improper Riemann integral, right. So, these things you already know, right. So, now we know how to integrate a function over an integral with respect to a variable, right. So, now we are going to generalize this theory of integrals, okay, to what are known as abstract integrals. Okay. So, what we really want to do is to define something like this. Okay. So, this primer is over, this primer on Riemann integration is over. Suppose, so this is called, so we are getting into abstract integration. Here let omega f mu be any measure space, not necessarily even a probability space, be a measure space, and f from omega to r, well actually I can have from omega to 0 infinity included, f from omega to infinity be a measurable function. Okay. So, you have some omega f mu, this is your omega, right, and you have a sigma algebra on it and some measure on it, this may not even be a probability measure, okay, some measure, and then you have a function that maps omega to real line, or it can even some points can even map to plus or minus infinity, right, that is allowed. Okay. So, f in certain points can even take plus or minus infinity as values. We want to define the following abstract integral. Okay. So, we want to define integral f d mu over a measurable set A. Okay. So, you have a measurable function from omega to r or omega to r union plus infinity minus infinity. You want to define the integral of a measurable function with respect to a measure over a measurable set, f measurable set. Okay. So, that is what we will define. I have not I have not defined it, I am saying this is what I want to do, right. So, from now on you will not think of integrals as integral over an interval and integral with respect to a variable, okay. That is high school or undergraduate stuff. So, as graduate students we will think of integral as integral of a measurable function with respect to a measure over a f measurable set. Okay. From now on this is how we will think of it. Okay. I have not told you what it is of course, but that is where I am building. Okay. I am just saying what we want to do. Okay. So, this is called abstract integration. Now, so why are we bothered doing this? So, the reason is this naturally generalizes the concept of a Riemann integral to include more general measures as well. Okay. In particular, so let me put down a couple of special cases. I will put two special cases down which are very important. So, let us say that omega f mu is simply r Borel lambda. Okay. So, this guy is RBR lambda, Lebesgue measure lambda. So, in that case my integral will be integral f d lambda over a, right. So, A will be some, so what kind of a set? A will be some Borel set, right. So, you are integrating a measurable function with respect to the Lebesgue measure over a Borel set. Okay. So, here A is Borel. So, this integral is known as the Lebesgue integral. Okay. So, it is integral with respect to the Lebesgue measure, therefore, the integral is known as the Lebesgue integral. Okay. So, this Lebesgue integral naturally generalizes the Riemann integral. Okay. So, this is like saying I am going to integrate f is after all a function from R to R now, right. So, you are integrating a function with respect to the Lebesgue measure over any Borel set. So, here you are doing the same thing except the set you are integrating over is it is a particular interval, it is not some general Borel set, right. So, what this does is generalizes the concept of a Riemann integral. So, in fact, we will see that there are you can integrate. So, the Lebesgue integral is defined for certain functions over more complicated sets, and it is defined even when the Riemann integral is not defined or when the Riemann integral may not exist even, right. So, the Lebesgue integral exists sometimes even when the Riemann integral does not exist. Okay. But however, the nice thing is whenever the Riemann integral exists, the Lebesgue integral always exists. Furthermore, the value of the Riemann integral will be equal to the value of the Lebesgue integral. Okay. So, in that sense this is a strictly more general notion of an integral of a function from R to R. Okay. I have not told you what it is of course, but I am just building up towards what it is, right. So, Lebesgue integral this generalizes so I will just say it generalizes the Riemann integral in the sense that this may exist even when the Riemann integral may not exist, but when the Riemann integral exists the Lebesgue integral always exists and the values will be equal, right. So, in some sense we can, from once I have told you what this is, you can totally forget about Riemann integration because this is strictly more general. Okay. So, in the beginning this may seem like a little abstract because it is called abstract integration after all, but once you learn Lebesgue integrals and abstract integrals in general, you will actually feel that the Riemann integral is a very awkward integral. It is actually quite awkward and it does not exist for even fairly simple functions. Okay. Okay, that is the first example of an abstract integral, right. It is the Lebesgue integral. The second example we consider the space omega f mu to be a probability space. So, mu will be a probability measure now. Okay. So, we will consider, since we are doing probability theory, so let us say this is a probability space, mu is a probability measure now. So, I call it P. Okay. and I am going to consider a measurable function from omega to let us say r. Okay. Consider a measurable function from omega to r, but what is a measurable function from omega to r? It is a random variable, right. Now this is a probability space. Consider a, so I will just say consider a random variable, right. Consider a random variable x from omega to r. Okay, this is a special case of a what we have written down there, right. Fine. So, now the integral will look like what? Consider, I am going to consider integral, I am going to integrate over the whole space now. Okay. So, this is you can integrate over any f measurable set you want, right. I am going to integrate over omega itself now, omega is f measurable. So, I can integrate over omega, this is a special case, right. What will the function be? X d p, right. This p is my measure now. Okay. By the way, a matter of notation, whenever I integrate over the whole space omega from now on, I will not write omega here, I will only write integral, right. I will not actually, I will do that when I write integral f d mu without saying what set I am integrating over, it is to be understood that I am integrating over the whole space omega. So, let me just write integral x dp from now on, the omega is implicit here. Okay. So, this integral is of great importance in probability theory. Okay. So, this integral is called the expectation of the random variable x. Okay, and it is denoted by E square bracket x. Okay. So, given a, so this integral will be some number, right, and this number is called the expectation of the random variable x. Okay. So, so what is the expectation? It is just integral x dp, but I have not told you what integral x dp is, right. So, once I finish telling you what integral f d mu is, you would already know what a Lebesgue integral is, you would already know what a expectation is. Okay. With me? So, these are just special cases of the abstract integral, integral f d mu. Okay. Any questions on this? Okay, so now we will actually go to build towards defining this. I have not told you what it is yet, right. I only told you what special cases we have. So, I have, so let us follow the following agenda for defining this abstract integral.